Okay, good morning. Before starting the lesson, I sent an email regarding a math competition. If you have already received that, that's good. If you haven't received that and you are interested, let me know that I can pass you the information, okay? So the date will be next Tuesday, but you need to inform me if you want to join so that I can arrange by Thursday, okay, this Thursday. Okay, now we want to continue the lesson. The division algorithm is actually one of the most important theorems in number theory, and understanding it is easy, but proving it is a little bit hard, and the proof is not in the book. So you have to trust me on that it's going to work, okay? So let me phrase it here for you. Let so let me underline that so you don't get confused. This is not the article A, it's A. Let A and B not equal to 0 be integers. Yes? And there exist unique integers I'm sorry. There exist unique integers Q and R such that A is equal to B times Q plus R, and 0 is less than or equal to R is less than absolute value of B. Okay, so these integers are unique. So what we can, if I want to summarize this in mathematical symbols, I would say that for all A and B not equal to 0, in the set of, so let me write it like this, B not equal to 0 in the set of integers, there exist, when I want to say there exists, I use this, but if I want to say there exists a unique, I put an exclamation mark there as well, Q and R in Z, such that A is equal to BQ plus R, and 0 is less than or equal to R, less than absolute value of B. So you don't need to be worried about that, but if you're interested in writing everything in mathematical symbols, that is how you do it. So for all A and B, B not 0 in Z, there exist, exclamation mark means unique, Q and R in that one, okay? So let me just describe. This seems very hard, but it's a very, very simple thing. So let me choose A for you to be, I don't know, 23. Let me choose B to be 5, okay? So essentially what this is telling you is that as soon as you choose two integers so that the second one is not 0, you can always write the first one as a multiple of the second one plus another number R, so that this R is greater than or equal to 0 and less than absolute value of your number B, okay? So for example, can you find those numbers? It is very simple. So if I ask you to divide in your head 23 by 5, how many complete 5s you can find in 23? 4. Okay, so this becomes 5 times 4, and how many is left over? 3. Okay, now do you see that I was able to find Q and I was able to find R? The R that I found satisfies this condition as well, because the absolute value of 5 is nothing except 5, and the number R that I found really satisfies this condition, yes? 3 as on the one hand greater than 0, on the other hand it is less than 5. This theorem claims that this is always possible. If you are given two integers A and B, whatever they are, first of all, you can find an integer Q, an integer R, so that this condition holds and this is also satisfied, but more than that, you cannot find any other numbers that you just found. That is unique. Okay, so you cannot try to find other numbers. Of course, you can try find other numbers, but you cannot find other numbers satisfying this condition. For example, I can say that 23, I can write it as 5. Instead of multiplying it by 4, I multiply it by 5. It becomes 25. Then I have to return back to 23. So I need to add how much? Minus 2. Okay, so I was able to write it in this form again, but you see, if I insist to keep this condition the case, this is only 4 and 3. You see, minus 2 plus 5 times 5 is really 23, but minus 2 does not satisfy this condition. Yes? So if you relax that condition, the uniqueness is gone. You can find infinitely many pairs of Q and R satisfying this equation. For example, can you give me another one? Let us say I want to relax this condition. Can you find something more for me? 5 times 3 and then? Plus 8. Very good. You see that this is again 23. But this number 8 satisfies the positiveness, but does not satisfy this condition that it should be less than 5. So long story short is that if you want to find integers Q and R, and you also simultaneously want to respect that condition, then mathematician has shown that there is only one unique Q satisfying this condition and one unique R satisfying that condition. And when that is unique, in mathematics, when something is unique, it is good to give it a name. This number Q is called the quotient of division of 23 by 5. When I divide 23 by 5, the quotient is 5. The remainder of this division is 3. Okay? So when I write this number like this, it is good to know about that. So these are the names, so might be you face. So BQ plus R. Extremely important is that if it satisfies this condition, okay, then you can call this the quotient. Then this is called the remainder. So I have to write the article there, but I'm lazy to write it all the time. But the quotient, the remainder. And there is a name for this one. This is called dividend. And this is called divisor. Okay, so there is a little bit unfortunate name here, because when I say divisor, you expect that they should be divisible. But no, I mean, in this context, this is also called a divisor. Any questions? So for example, here, if I ask you, what is the remainder of 23 by 5? You have to first write it in this form so that this number satisfies the condition. Then you read this one as the quotient, read this one as the remainder. As simple as that. Yes, is that clear? Okay. So let me give, I know that this is good to have some very trivial examples. So let me give this immediate example right away. So in each case, determine the quotient and remainder of A by B. Okay, so I'll write some of them. I want to wait for you to solve it for me, okay? So in each case, I give you two numbers, one for A, one for B. In each case, I want you to determine the quotient and the remainder if you divide A by B. It's just a very simple calculation. I want to make sure that you understand and respect the conditions here. So the first one, let me just write the same thing. We already did that, of course. Let me write number 2 here. So let me choose the numbers that I wisely designed here. So A is 28 and B is minus 6. Number 3, you don't need to wait for me, you can start doing them as I am writing. A is minus 31, B is 7, minus 25, minus 3. So I give you a little bit of time to think. So in each case, you have to write A as in this form with the given B, but you have to also respect the number that you choose for R should satisfy that condition. As far as you are done, this is guaranteed, it is always possible, but it is also guaranteed that it can be done only in one way, okay? No, I am respecting the same notation here, yes? So this R should be greater than or equal to 0 and less than absolute value of B. And in each case, A is this A and B is that B. Yes? Yes? Now someone is knocking? Okay, good. So let us just do it together. So the first one is actually extremely simple. It's exactly, let me just write it for completeness. So A is equal to 23, so I write 23. And I write B, which is 5. Then I try to find Q and R so that, first of all, this works if I put that in that relation. Secondly, that I have to respect the second condition, so that is important. So this was easy, yes? So what was that? So you write 23 is 5 times 4 plus what? Plus 3. And this 3 really satisfies the desired condition, meaning that this is greater than or equal to 0, and it is less than absolute value of B, which is 5, yes? Absolute value of a number is the magnitude of the number. So this is true, so then it means that, yes, what can you conclude? You can conclude that Q, the quotient, is 4, and R is 3. So we want to repeat the same process for those pairs. And sometimes when the numbers become negative, you have to be a little bit careful not to get confused, okay? So for example, number 2, did you do that? So 28 is A, and B is what? Minus 6. Then you have to guess something here and something here, okay? So what are those numbers you found for me? Could you do that?
Minus 4.
If you put minus 4 here, let us see if it works. If you put minus 4 here, so far it is 24. What you need?
4.
You need positive 4. Okay. Is it enough? But you have, yes, you have to check. That is correct, I think. So if this number 4 should be greater than or equal to this number, which is correct, it should also be less than the absolute value of your B. Your B is minus 6. So absolute value of B is how much? Is 6. Is that true?
Yes.
Whenever it is true, it is guaranteed this is the only choice. So don't look for other answers. Yes. So what you say for Q then? Q is negative. Yes, Q is negative. But what is R? Positive 4. So the quotient is minus 4, but the remainder is positive 4. The remainder cannot be negative, but as you see, the quotient might be negative, might be positive. So number 3, A is minus 31, B is 7, so I need to fill it up. Something here, so it works and it respects the condition. Could you find that?
So did you say the remainder can never be negative?
No. The remainder is R, and as you see, that's the condition. So what, did you find the Q and R here? Yes?
Q is minus 5.
Q is minus 5, exactly. So you have to go a little bit beyond that, then come back again. Yes. So what is that? What is r? Plus 4. First of all, you have to respect this. Is it fulfilled? Yes. 7 times minus 5 is minus 35, plus 4 is really correct. And then, more than that, 4 that you found here is greater than or equal to 0, and it is less than absolute value of b, which is 7 here. That's correct. So no one will ever be found in something else. So that is for sure. Q is negative 5, R is positive 4. And the same thing for the other ones. Let us just do it quickly. So number 4, A is minus 25, B is positive 3. So Q and R. So what are they? What is that? Oh, that's minus 3, or what is that? That's my mistake. That's minus 3. I didn't see that. So what should be Q and R here? Yeah, Q is 9. But what happens? You go beyond minus 25. You return back by adding 2. And then, is it correct? Yes, because this 2 that you have here is really greater than or equal to 0, and it is less than absolute value of your b, in this case 3. Is that right? Yes. So you found the correct numbers. Q is 9, R is 2. So we say that the remainder of the division of minus 25 by minus 3 is positive 2. Okay? So making this right is one part of the story. Another part is making the other condition right. Yes? And finally, so let us just do that one. 5, what is that? A is minus 15. Yes? And it is minus 3 here. So can you tell me what is Q and what is R? Q is 5. It works, but then there is nothing left for R, so R should be 0. Do you agree with this equality? Yes? And do you agree that this can this can be the remainder? Yes, because what I need for this to be remainder is that this should be, on the one hand, greater than or equal to 0, which is correct. 0 is less than or equal to 0 is the correct statement. It should also be less than the absolute value of b, which is correct again, because absolute value of minus 3 is positive 3. So if I ask you what the quotient is, the quotient is 0. And if the quotient is 5. Sorry. The quotient is 5, but the remainder is 0. Okay, and finally the last one. Be careful. I am not telling you divide the bigger one by the smaller one. I want you to divide A by B all the time in the problem. Yes? So you write 7 on the left, 15 on the right, and then you have to fix Q and R for me. So what is Q and what is R here?
Q is 0.
Q is 0, exactly. But what is if Q is 0, then I have to have it what? 7, because I want to keep the equality. First of all, I hope that you agree with me that's correct. 15 times 0 is 0, plus 5 plus 7 is 7. So this is indeed correct. On the other hand, does this satisfy the condition for being a remainder? Yes, because 7 is on the one hand greater than or equal to 0, and it is smaller than the absolute value of 15. So here the quotient is 0, the remainder is 7. Yes, so this means that the quotient is 0, the remainder is 7. Yes? And then, of course, this is always the case. If you have two positive integers, one of them is smaller than the other one, so then the quotient is always 0, and the remainder is the smaller number. That's always the case, yes? Be careful, I am not dividing 15 by 7. So if I ask you 15 by 7, so then 15 becomes 7 times 2 plus 1. So the quotient will be 2, the remainder will be 1. I am saying that divide A by B, okay? In the normal calculations, if you divide 7 by 15, it is not divisible, then you have to do the decimal points and things like that. But in number theory, these are the definitions of remainder and the quotient. Yes, please. Okay. So I was a little bit confused. Okay, so if you don't mind, let me check that one to 15. Yes, you are right. Yes. So that was my bad, sorry. Yes? Yeah. That's the same thing. So 7 is equal to 17 times 0 plus 7. And this 7 is really greater than or equal to 0 and is smaller than the absolute value of 17. So the quotient is against 0 and the remainder is 7. So this is something that you can have in mind. If a and b are natural numbers, not negative numbers, positive integers, if you divide, and if a is less than b, if you divide a by b, the remainder becomes always the smaller number, the quotient becomes 0. That is a rule, and that is easy to understand from what we did here. Okay, any questions so far? So it's very, very simple. By the way, geometrically, it is easy to understand. Yes, for example, let us say that I have a length. So let us consider a positive length. So let me assume that I have a length. So let us say that the length is a units. But of course, because we are working with integers, so let us say that this length has an integer length. Yes, this line segment has an integer length, I call it a. And let me also have a smaller length b. That's also an integer length. Okay? So how many of them I can fit here, that is called the quotient. How many complete one of them, yes? For example, if, I don't know if it is working like this, I will take that one, 1b, 2b, 3b. Okay, so I'm a little bit unfortunate, so let me make it a little bit smaller, okay? Okay, so if you see, I can take this and then try to fit it here in this length. 3 complete ones I can fit, but there is some left over. That complete ones, the number of complete ones is Q, what is left over is R. Something like that, okay? That is not hard to understand from geometrical point of view. Okay, but let us solve a little bit more interesting problems. I see it in the book, but these examples I want to go little by little and increase the level of difficulty, okay? So write this. If the remainder of A by 12 is, so let me write those numbers, is 10, then what is the remainder of A, the same A, by 6? In principle, I should mention that A is an integer, yes? Because whenever I introduce a letter, I have to respect that I have to mention what A is. But because we are working in number theory, I told you that all the numbers that we are working are integers unless otherwise mentioned, yes? So this is an integer. So that's a very simple question. I am telling you that there is a number A, we don't know what that is, but we know that when we divide it by 12, the remainder turns out to be 10. Now I want to take the same number A, but instead of dividing it by 12, I want to divide it by 6, and I want to know what the remainder is. Okay, so that's a very simple, typical question in this regard, the division algorithm. Okay, so let us do it together. So if the remainder of A by 12 is 10, this English sentence can be written more compactly in mathematical notation. So this means that A can be, so you divide A by 12, you get a quotient, you don't know what the quotient is, no information you can find in the problem, so you just write Q, but the remainder is given in the problem, which is 10. So if I want to write it fine, so I say that there exists a Q in Z such that A when divided by 12 gives me remainder 10, and I don't know the quotient. It is not given to me in the problem. So that is the translation of that English sentence. Yes, this is what we know. Okay, so then you go to a scratch paper to discover a strategy. Yes, what is your strategy? You want to write A and divide it by 6, exactly as we did before for numbers. So you write A on the left. What do you want to have on the right? This time you're supposed to divide by 6. So you are looking for some Q and some R, yes? If you are able to write A as 6 times some integer plus another integer, then if you can guarantee that this R is greater than 0 and less than absolute value of 6, then this number is your answer. Yes? Is that clear? That is what we want to do. If I succeed to write A as 6 times an integer plus another integer, so that that integer is on the one hand non-negative, on the other hand less than 6, by that theorem, it is guaranteed that this number is definitely the remainder. Okay, so now you have something in mind. Okay, so I want to see how many of you have now a little bit of experience in working number theory, okay? So this is what you have. This is what somehow you want to aim for, okay? So how can you manipulate this one so that it becomes closer and closer to what you want step by step? Yes? Can you speak louder, please?
It's like you said that A equals Q.
Yes?
It's the same A, so A in that.
Yes, the same A. I cannot, yes.
So they are equal to 0.
This A is the same A. So this tells you that I have a number, I call it A. I know when I divide it by 12, the remainder turns out to be 10. I take the same A this time divided by 6. I want to see what the remainder is. You wanted to say something, maybe?
I wanted to suggest that
Yes. Suggest it louder, please. Yes.
with the factor of 6 from 12Q. 6 2Q.
Yes. So you see, if you have studied what I'm saying, even though there is nothing standard here going on, but it is not something completely extraordinary. So if you have listened to what I said, little by little, you understand what. So you understand by that way, I want to have this 6, but this is 12. Okay, I need to find a way to get rid of 12 in favor of 6, and there is one way probably to think about. After I do that, I write 6. And then I give 2 inside so that I cannot look it. You cannot just write 6. You have to do it in legal way, yes? And 10. Okay. Now you have enough experience. Can I call this capital Q? The only thing that I need to know in number theory to give it a name is that if this number is an integer, is it guaranteed that 2Q is an integer? Yes, because Q was an integer. If you multiply it by 2, it's an integer. So in principle, I can call it this. But then I can say that, okay, I have it, my number, R is 10. Is that acceptable? No, because I need 2 conditions to satisfy. So one condition, of course, you are right. If you don't care about this, you are right. You can say R is 10. But you also have to care about this, which unfortunately 10 does not work for it. Yes? If you put 10 here, 10 is greater than or equal to 0, right? But 10 is not less than 6. So this 10 will not serve. Okay? And then I hope that you have enough experience to know what to do. So you realize that you have to manipulate it a little bit more before calling this capital Q. What should I do? First of all, I want to write something which is exactly the same thing, written in a different way so that the number left over satisfies that condition. Yes? 6 plus 4. Yes? So what you do, you write it as 6. By the way, these things are not hard, okay? Right now, it is not hard. You have enough experience if you're really studying, okay? Instead of 10, I write 6 plus 4. What was the motive behind that? Because I can now absorb this 6 here. I don't care what happens here. What I care is that it remains integer, okay? But what I care is that this number should be less than the absolute value of 6. So this will serve the purpose, yes? Because if I take 6 out, it becomes 2q plus 1 and then plus 4. Can I still call this capital Q? Why? Because q is an integer. 2 times q plus 1 is guaranteed to be an integer. And now, what is the good benefit of doing such a strange thing apparently is that now this number which is left over, so let me write it down, I have 6 times capital Q plus 4. And this 4 really satisfies the condition that I demand, yes? And that is this one, okay? And now you are in a good shape, so you can say that what is the remainder? The remainder is 4, okay? So the remainder is 4. Yes? And then this is not a coincidence. But can I say something about the quotient? No, because I don't even know the quotient here. Yes? But one thing I know how the new quotient is related to the previous quotient. How they are related? Yes, the new quotient is 2 times the old quotient plus 1. And you can, by the way, check it for a number. I don't know. For example, let me take it 30. Let me take A to be 35. No, 34. Okay? If you divide 34 by 12, what is the remainder? It's 10. Yes? You divide 34. How many complete 12s you can fit in 34? 2, which becomes 24. How much is left over? 10. So that is correct. The number that you see is really satisfying the condition given in the problem. Now, instead of dividing this number by 12, divide this number by 6. Your calculation tells you that the remainder has to be 4. Let us check. If I divide this by 6, how many complete 6 I fit into 34? 5. 5 times 6 is 30. And what will be the remainder? 4, as predicted. And this is not a coincidence. Not only 34, any other number satisfying this condition will give you remainder 4 if you divide it by 6 rather than 12. Okay? And then do you remember what was the quotient in the second case? The quotient in the first case was, if you divide by 12, the quotient was 2. In the second case, the quotient was 5. And that is right. 2 times this plus 1 more. The relation between the quotients are right. So this is a typical problem. It's not hard, by the way. Is there something you don't understand? Okay, so let me increase the level a little bit. Okay, so, and I won't wait for you this time because you have enough experience now. So let us clean this. Okay, so example. The remainders of integers a and b by 19 are 3 and 17 respectively. Determine the remainder of this combination 2a minus 3b by 19. Yeah, to be honest, if you can solve this problem on your own, you are completely on the safe side. You understood whatever you need and you are enough creative here. Yes, yes. So let me double check. The remainders of integers a and b by 19 or 3 and 17 respectively. determine the remainder of this combination, 2a minus 3b, by 19 again. You see, I have two integers a and b. I divide a by 19, the remainder turns out to be 3. I divide b by 19, the remainder turns out to be 17. Now I take the same a and the same b and I construct this new number, 2a minus 3b, and I want to divide it by 19, and I want to see what will be the remainder of this new division. Yes? What I will do, I will write with some more problems, so if you can solve that problem, don't waste your time, you can go to the next one. Then we solve them together, okay? Okay, so now let us try to see how it is going for you. So this example tells you that we have two integers a and b. When I divide them by 19, one remainder is 3, the other remainder is 17. 3 is for a, 17 is for b because of the word respectively. And then determine the remainder of this combination by 19. Yes? So let us translate these English sentences into mathematical symbols. So you know that when you divide a by 19, the remainder that you get is given in the problem to be 3. Yes? But you don't know anything about the quotient, so you just write the quotient to be q, and you just write there exists a q in z. Yes? And now translate the second one. If you divide b by 19, so what do you write? 19, but you know the remainder. The remainder is 17. So what should I write for the quotient? What? Everyone? So be careful, you're not allowed to put the same q, because there is no guarantee that the quotients are the same. So you have to change the letter. So let us change it to q prime. So if you have done it with q, that's wrong. Be careful. Okay? So the second, when you say the second one is also q, it means that somehow you know that the quotients are the same, but you don't know. They might be the same or not. Okay, so this is what you know. But what you demand is dividing this by 19. So if you go to a scratch paper, what is your goal? Your goal to have this number on the left. You want to have this 19 on the right, something times q plus r, but more importantly, r should satisfy this condition, yes? Absolute value of 19 is the same 19. So this will guide you what to do. This is what you do in a scratch paper, okay? So now I don't think at least the starting part is hard. What is the starting part? You have two pieces of information, one for a, one for b, but you want to have something about 2a minus 3b. What is the natural step to do, to take? Yes? Yeah, exactly. I start making that combination using my information here. So I would say that, okay, 2a minus 3b is a number that I want to say something about it. Okay? How can I do that? The only thing that I have at my disposal is this piece of information, yes? So what I should do, I replace a with that given number, that given expression. This is the only thing I can do, yes? Minus 3 times this one. Okay. So this is the first thing comes to my mind. By the way, it was not that hard, yes? You want to say something about 2a minus 3b. The next step is probably also natural, because in mathematics we try to simplify things if possible. So we expand. So when we expand, 2 times 19, so you have enough experience. Let me just write 2 times 19. I don't even bother to multiply things out, because I have something in mind. I want to have 19. I want to have 19 manifest itself in my calculations. So 19 should be there, yes? So 2 times 3, if you want, you can multiply, of course. 2 times this and times q. 2 times 3 is 6, and minus 3 times that one. So let me write it the same story. It's minus 3 times 19 times q. If you prefer, you can multiply. And minus 3 times 17 is minus 51. But still, I can simplify things more. So let me write 2 times 19q here. Let me write minus 3 times 19q prime here. And let me simplify these two, which is minus 45, yes? So it was very natural, it is not hard. But then you have something here, you want to have 19 as a factor. So this might motivate you to factorize 19 out, which is not bad, then it becomes 2q minus 3q prime, and then you have minus 45. And of course, if you want, you can call this capital Q. It is guaranteed that this is integer. Why? Because q and q prime are integers, so this combination is definitely an integer. But there is one problem here. So if you just do it right away and write 19q, and then you write plus minus 45, you cannot tell that, okay, this number is the remainder. Why? Because it is negative. The remainder should be positive and less than 19. So even though what you have done is completely correct, minus 45 is not what you can guarantee as a... minus 45 is not something that you can offer for the remainder. Okay? And now, but of course you have a little bit more experience now, so you know you have to start manipulating minus 45 in a way that on the one hand, it has some factors of 19 in it, so that I can pull it out and absorb it here, and then I have some leftovers which are positive this time. Okay? So this one I cannot teach you how to do that because these are simple numbers, sorry. So you have to be able to do it yourself. So I would recommend you not to take 19 at this step because you see what the problem is. So let me clean that and wait for you to tell me what to do. How should I manipulate that? Okay, can you tell me what should I write instead of minus 45 so that on the one hand, I can absorb multiples of 19 to these multiples of 19, and then what is left over has this condition to be non-negative and less than 19. So what are the multiples of 19? 19, the other one is 38, the other one is 57, and I don't think we need more than that. So the numbers that you need is on the board. Can you manipulate minus 45 in that way? Yes?
Minus 57 plus 12.
Plus 12. You have to go back, yes? So what you write, I write minus 57, which is 3 times 19. But then I have to go back to minus 45, so I have to add 12. But now I hope that you see that this is really working. Why? Because this one and this one and that one, I can pull 19 out. From here, 2 times q is left. From here, minus 3 times q prime is left. And from here, 3 is left. And then I have plus positive 12. Can I still call this capital Q? Yes, because this becomes an integer. Yes, this new combination is also an integer. So this becomes 19 times q plus 12. But on the other hand, 12 is really greater than or equal to 0, and it is really less than 19. So yes, this is the remainder. Yes? Is that understandable? So it was not hard, to be honest. It's not, but these problems can be sometimes hard. I don't want to increase the level of difficulty because I want to keep it the same level as the level in the book. But this is something, and then later we will learn something better to find the remainder. But learning this is also part of the course. So is that clear? Okay, so now let me see how much time we have because I have to continue this one. Okay, but before solving that, because I want to make sure that I will be able to finish what I'm supposed to finish today, let me keep these 2 problems here on the board. So if you have time, after I finish what I'm supposed to say, we come back and solve it. Okay. So one thing that is important, I want you to know is this one. So let us consider the set of integers. The set of integers z, which you know is minus 3, for example, all integers, minus 2 positive or negative, minus 1, 0, 1, 2, 3, and etc. Let us imagine them to be in this box. Let me imagine these numbers to be on this vertical rectangle. Okay, so let me just choose a random integer, any number that you like. But for b, instead of choosing it random, let me just choose 2. Okay, let us see what happens. And I want you to write the division algorithm for these choices. A is arbitrary, but b is 2. What happens if I want to use the division algorithm? The division algorithm tells you that if you divide A by B, A is on the left, B, which is 2, is on the right, then you will have some Q, and then you will have some R, yes? But Q and R are not only integers, but R also satisfies an extra condition, and that is greater than or equal to 0 and less than absolute value of B, but absolute value of B in this case is 2, yes? So what I am just doing, I am rewriting the division algorithm for an arbitrary number A, but B to be 2. That's nothing, I'm just replacing it. But how many options I have for R? 2 options, because R is an integer. So what are my options? Either 0 or 1. If R is 0, what do I get? I get A is 2Q. If R is 1, what do I get? I get A is 2Q plus 1. So what does it mean? It means that whatever you choose from this set, that number is either a multiple of 2 or a multiple of 2 plus 1, which was already trivial to you, yes? Because multiple of 2 means even, multiple of 2 plus 1 means odd. So what I just told you is that if you pick a number from integers, it is either even or odd. Yes? But that is a consequence of actually this one. So it means that this number 2 partitions this set into 2 floors. Okay, one floor are the numbers of this type, one floor are the numbers of this type. Yes? So what happened, I partitioned Z into 2 non-overlapping groups. Okay, if a number is here, definitely this number is not there. If a number is there, it is not here. Okay, but in total, they build up this building of complex of these integers. Is that right? So you might say that, okay, we already knew about this, why we need division algorithm. So let us go to the next step. So at first, I want you to understand, then I will give you some examples, which is the application of. Now, let us just do the same thing. This time, I take an arbitrary A, but let me change my B from 2 to 3. Okay? And then do the same thing. So if I write the division algorithm for an arbitrary A, but B to be 3, how should I write it? I write A on the left. What do I write on the right? B is 3, Q is an integer, R is also an integer. But R should be where? Greater than or equal to 0, less than absolute value of 3. But how many options now I have for R? R is an integer on the one hand, on the other hand, it is sandwiched between these 2 numbers. So what is R? Possible options for R: 0, 1, and 1 at 1 less. So you see, when I chose 2, the maximum R is 1. When I chose 3, the maximum R is 2. But the minimum R is always 0. Yes? Now what happens, if I choose R to be 0, then A is 3Q. If I choose R to be 1, then A is what? 3Q plus 1. If I choose R to be 2, then A is 3Q plus 2. Then what does it mean? It means that the same building of integers now, using this number, is partitioned into 3 different groups, non-overlapping groups. For example, let us say the bottom floor is 3 times Q, the middle one is 3 times Q plus 1. I want you to understand what is the meaning of this diagram. What is the meaning of this diagram? It tells you that whatever number you choose in integers, it is either a multiple of 3, or a multiple of 3, 1 more, or a multiple of 3, 2 more. But that is the consequence here. In this case, multiple of 2 plus 1, we have particular names for them, even, odd. We don't have particular names for these numbers, but this is the way that you need to imagine. Is that clear? Okay, and this is important. If a number is here, it is not there, it is not there. There is nothing in common. There is no intersection. There is no overlap between them. Okay, and then let me continue one more. Be patient a little bit. So let us just do it for an arbitrary A, but let me change B from 3 to 4 this time. I hope that you imagine what's happening now, yes? So if I have an arbitrary A, but this time I choose B to be 4, then A is equal to B times a Q plus R, but the options for R are also limited again. So what are the options for R that I have? Either 0, 1, 2, but maximally 1 unit less, it's 3. Okay, and what happens if R is 0, you get A is equal to 4Q. If R is 1, you get what? A is 4Q plus 1. If R is 2, you get A is equal to 4Q plus 2. And if you get R equals to 3, you get A is equal to 4Q plus 3. And then what if you want to imagine it from diagram point of view? Then how many floors you have? The same building? Yes, because the building is the totality of these numbers, but now it is being divided into 4 floors. Yes, for example, the bottom floor is what? 4Q, the next floor is 4Q plus 1, the next floor is 4Q plus 2, and the final floor is 4Q plus 3. Okay, so what does it mean? It means that if you choose any number, either that number is multiple of 4, or multiple of 4 plus 1, or multiple of 4 plus 2, or multiple of 4 plus 3. Okay? So, is there something that you don't understand? It's very, very simple. Okay? So you might say that, okay, what's the benefit of that? We come to it. So let me tell you something else. This is the same building. Okay, I couldn't draw identical diagrams, but this building is the same building there. So it means that if I have a magnifier, if I have a lens, which 2 is written on it, when I keep it on the set of Z, I see two floors. 1 floor even, 1 floor odd. But if I take that magnifier and replace it by a magnifier labeled 4, if I see the same building, then these numbers will be divided into 2 more categories, and these numbers will be divided into 2 more categories. Okay, so let me ask you something. The numbers here, do you think are even or odd? If a number is multiple of 4, it is automatically a multiple of 2. So whatever you see here, if you go here, looking it with the lens 2, you will see it here. Okay? But this one, so these numbers are going there, and these numbers are also going there in the bottom floor, yes? Why? Because 4Q plus 2 is also even, yes? If you multiply a number by 4 and add 2 to it, it becomes again even. So if I take the magnifier with label 2, I only see 1 floor containing the even numbers. But if I have the same magnifier with label, so not the same, the magnifier with label 4, this itself will break into 2 parts. Yes? One part, let me change my letter because I have used letter Q here, so it becomes 4K, and the other one becomes 4K plus 2. And if I take and look here closer, and then I will see the other ones are odd, yes? 4Q plus 1 is odd, 4 times Q is even, plus 1 is odd, the same thing here. So this will be break down into 2 more ones. So it becomes 4K plus 1 and 4K plus 3. Yes, is that right? So that is the story. So instead of choosing 2, 3, and 4, let me just choose A and any B. So how many floors do you think I will have? If B was 2, I had 2 floors. If B was 3, I had 3 floors. If I have 4, I have 4 floors. So if I have B, how many floors I have?
B floors.
B floors, okay? And the one, but B starts from, the R starts from where? Always from 0, maximally up to 1 unit less. So it goes up to B minus 1. Okay. Is that clear? Okay, so let me ask you some question. Let me say, okay, let me write it for 5 as well. For 5, I don't want to write the details. So the first floor is 5Q, the second floor is 5Q plus 1, the next one is 5Q plus 2, and then 5Q plus 3, 5Q plus 4 is the last one, yes? 1, 2, 3, 4, 5, yes? Now let me ask you one question. I take one number from this floor. By the way, how many numbers are in this each floor? Infinitely many, yes? So I take one number from this floor and one number from this floor and multiply them. In which floor will be the product? This is a question that I want you to understand. It is a very simple problem. So you see there are infinitely many choices that I have here. I pick one of them randomly. I have infinitely many choices that are here. I pick another one randomly. I multiply these two, it becomes a number. That number has to be in one of these floors because there are no options left. Yes? This is important. By doing this, there is no room left outside Z. This is the whole Z. In each case, all the numbers you see here are here. So there is nothing outside it, yes? So if I take two integers, one from here, one from there, multiply them, it becomes an integer. It has to be here. So it has to be in one of them exactly because there are not overlapping things there. But my question is that where it will be, in which one of these floors? Yes?
5q plus 1.
Okay, can you tell me why?
Because
First of all, you can choose an example in your head. Okay, can you give me an example of a number in this floor?
22.
22. But you chose a big number. Okay, 22. And not big. Why? Everyone agrees that 22 lives here. Why? Because the numbers living here are multiples of 5, 2 more. 22 is multiple of 5, 2 units more, yes? So you are right, 22 lives here, yes? Can you tell me another number? Please make it small so that I can multiply it in my head. Okay, can you give me a small number there? 20? 13. Yes. So 13 is also there. Everyone agrees? 13 is here. 22 is here. Yes? Why is that? Because 13 is a multiple of 5 plus 3. What is that multiple? 2. If you put 2 here, 10 plus 3 is 13. So 13 is one of the numbers in this floor. And 22 is one of the numbers in this floor. And if you multiply them, so what happens? So 1, 4, 3, and 286, I think, yes? So then 286, we need to see where it is. How should I know where it is? How do you know where 286 is? Are you with me? Hello? Yes? So how should I know that in which floor 286 lives? Yes, please. Pardon? Yes, you divide it by 5. For example, let us have the calculator. By the way, you don't need to divide it because 286 is 280 plus 6. Yes? So this is a multiple of 25, so forget about it. And then what is the remainder of 6 to 5? How many 5s you can fit in 6? 1. And what will be the remainder? 1. So yes, this lives here. Because this is because 286 can be written as 285 plus 1, agree? And 285 is a multiple of 5 plus 1. So 286 lives there. But my question is that, do you think it was a coincidence? Or is it always true that if you pick a number from this floor and a number from this floor and multiply them, it becomes a number in this floor? Yes? Now, you wanted to say something, yes? Do you know how to prove this?
I just had a vague idea.
Pardon?
I just had a vague idea.
Yes, just tell me the vague idea.
So I thought of Q, like you can always factor out something Q, and so 2 and 3 always like something.
Oh, yeah, it's not very hard, by the way. And so your intuition was at least correct. But what you want to do it formally, you need to pick a generic number from this floor. Can you give me how should I write? A number in this floor is 5 times Q plus what? 2. So I say that, okay, let me pick a representative. Let me pick a representative from this floor. Any number in this floor is a multiple of 5 plus 2, yes? So let us say that that is the number that I picked. And now let me pick another representative from this floor. How do you name it? How do you name it, please? Are you with me or not? Hello. So what is the name of this number? What can I call it? If I pick a number here, any number here is a multiple of 5 plus 2. So if I pick a random number from here, 22 is one of them. Okay, I cannot say this is definitely 22, but I know something. Any number that I pick is 5 times an integer plus 2. Is that right? Okay. Now I want you to pick a generic number from this floor. How do you read it? What is that number? What?
5 times an integer
Plus 3. But this is not correct if you write 5q plus 3, because then you are forcing these q's to be the same. So you have to write it as q prime. Okay? So this is a typical member of the third floor. This is a typical member of the fourth floor. And then you multiply them. Yes? Because I asked multiply them. So you start multiplying. Very simple algebra. So this 25 q prime plus 15 q plus 10 q prime plus 6. Yes? But you know what is your goal. You want to see this number lives where. So you need to know, you need to pull out factors of 5 and see how much remains so that you can point out the floor. Yes? So how should I do that? You immediately see that these are multiples of 5 already. But if I pull 5 out, then something here, and then 6 is left. But 5 this plus 6 is none of those floors apparently. So you know what to do. You need to take this 6 and write it as 5 plus 1. And now you can factor 5, 5, 5, 5 here. So this becomes 5q prime plus 3q plus 2q prime. Yes, and then plus 1, and then finally plus 1. Yes? But you see that you have enough experience in number theory by now, hopefully. You don't care how big this is. What you care is that, is it an integer or not? Is it?
Yes.
Yes, because q and q prime are integers. So you can call them, I don't know, a new q. So then it becomes 5q plus 1. Okay, and then where 5q plus 1 lives, it's a multiple of 5 plus 1. So it lives in this floor. So it was not a coincidence. Yes, I took two representatives of these in general, multiplied them, and I convinced myself that the product can be written as the form of 5 times q plus 1. Yes? Are you with me or not? Hello? Okay? Now, you might say that, okay, what is the point of this? Let me give one example and then we'll finish. If you are interested, we can probably start solving those problems next session. So what I want to solve, this is the important example that you will learn why this algorithm is important if you understand it in that way. So what I want to show is that you know that we don't know that much about prime numbers even yet. So we don't know how they are distributed. But what we want to claim is this. Show that, this is a very important example, show that every prime number greater than every prime number greater than I think 3 is either a multiple of 6 plus 1 or a multiple of 6 minus 1. Minus 1. Which is not trivial at all. Okay? Because we don't know exactly how can I generate all prime numbers. Be careful. It is not telling you that every number which is a multiple of 6 plus 1 or minus 1 is a prime number. No. I told you P implies Q does not guarantee Q implies P. So be careful. This only works in one direction. I am claiming that if you pick a prime number, okay, which is greater than 3, it is either a multiple of 6 plus 1 or a multiple of 6 minus 1. And that is a big claim because we don't know all the prime numbers. But we are claiming such a big claim here, yes? We're saying that no matter what happens even in the future, what prime numbers we will discover, that prime number has to be multiple of 6, 1 more, or multiple of 6, 1 less. For example, let us check 17. 17 is a multiple of 6, one less or one more?
Unless
One less. Because multiple of 6 is 18, one less is 17. Be careful, it is not claiming that every number of this form is prime. This is claiming that if you have already a prime number, this is either this form or that form. Okay, for example, another number, 20, what was that? 23, for example. It's a multiple of 6 minus 1 again. Yes? The other number, for example, 43. 43 is what? A multiple of 6 plus 1. So it doesn't matter which prime number you choose, it is either of these one. And it is not trivial, I want you to feel it. It's not that trivial thing we want to show. But let me try to prove it because we don't have time. The problem is, you need somehow, this number 6 indicates you to do something like this. You have your edifice, or whatever you call it, so then you subdivide it with 6. You take the length labeled 6, and then when you look at the set of integers, you will see 6 floors. Okay, can you tell me what is the bottom floor, for example, metaphorically? 6q, yes? What is the next floor? 6q plus 1. What is the next floor? 6q plus 2. What is the next floor? 6q plus 3, and 6q plus 4, 6q plus 5. Should I continue more? No. Yes, I have 6 floors. Okay. Now, I would say that let P be a P greater than 3, because it is mentioned greater than 3. Let P greater than 3 be a prime number. Okay, first of all, let me ask you why I excluded 2 prime numbers. One prime number I excluded was 2. Another prime number that I excluded is 3. Okay? Can you tell me where 2 lives in this building? Where 2 lives? No. The first floor is the multiple of 6. 2 is not a multiple of 6. So 2 does not live there. So where does 2 lives? Yes, everyone, where 2 lives? Yeah, hello. Yes? 6q plus 2, yes? Because 2 is a multiple of 6. Which multiple? 0 multiple plus 2. So 2 lives here. Where 3 lives? The next floor, yes? Okay, so I exclude this one. But I am telling you that I pick a prime number which is not 2, which is not 3. Whatever it is, I don't care. It's just a prime number. I claim that that prime number cannot live here, even if I don't know that prime number. Do you agree? Why that prime number cannot live here? Hello? Yes? Yes, because the numbers that are here are all multiples of 6. They cannot be prime. So the prime number cannot live here. Yes? Is it possible for your prime number to live here? Why not? 6q plus 2, yes, why not? Yes. Yes, so you cannot live here. Because 6q plus 2 is a multiple of 2. Yes? 6q plus 2, if I factor 2 out, it is 3q plus 1. So it is a multiple of 2. So a prime number cannot be a multiple of 2 if it is greater than 3. So this cannot live here. And there is another floor that I am certain about, that P cannot live there. Which floor is that? 6q plus 4. The prime number cannot live here. So there are only 2 options available for this poor vagabond P, yes? So where is it? There are 2 floors left, yes? This P, whatever it is either here or, can the prime number live here?
No.
Why is not?
It's a multiple.
It's a multiple of 3, yes? If you factor 3 out, 6q plus 3, if you factor 3 out, it becomes 2q plus 1. So it's a multiple of 3. A multiple of 3 cannot be prime. So my prime cannot live here either, yes? So there are only 2 floors left for this prime number, yes? Either that prime number is here or the prime number is there. Do you agree? Yes or no?
Yes.
If the prime number is here, okay, this is claiming the same thing. It's a multiple of 6 plus 1. So if my prime number that I choose which has to be either here or there. If it is here, I am already done because it is a multiple of 6 plus 1. Another option is that my prime number lives here. But do you see that 6q plus 5 and 6q minus 1 are the same things? Yes? Because if my prime number lives there, it means this is 6q plus 5. But now you have enough experience. Instead of 5, what can I write? I can write 6 minus 1. Agree? And then I pull 6 out, so it becomes q plus 1, and then I have minus 1. I can call this capital Q, so it becomes 6q minus 1. So every number of the form 6q plus 5 can be viewed as 6q minus 1 as well. So this poor prime has only two places to live, either here or there. If it is here, it's a multiple of 6 plus 1. If it is here, it's a multiple of 6 plus 5, which can be written as a multiple of 6 minus 1 as well. So then I am done. So every prime number is either a multiple of 6 plus 1 or a multiple of 6 minus 1. And this was highly non-trivial result. Yes, even though the proof was extremely simple and understandable, but because we don't know the list of all prime numbers, this is a very big claim to make. Every number that we can discover from now on forever, any prime number should be multiple of 6 plus 1 or multiple of 6 minus 1, even if we don't know what are they. Okay? So anyway, any questions? Okay, thank you very much. Just wait a little bit so that I can close the